All right, so here in 4.8, we're going to have yet another application of our matrices where we can use them to perform transformations. And this would be an application that works really well in like computer programming, especially with like gaming, okay? So kind of just in an elementary sense, I'm sure we're all familiar with like Pac-Man and Mario, right? So you can represent those figures on a coordinate screen with vertices, right? And you can perform transformations on those vertices within the figure in order to move it left, right, up, down, make Mario get bigger, make him get smaller, have him turn around, things like that, okay? The matrices are a really good way of doing that because you can store a lot of numbers in to represent a lot of different vertices very easily in them, okay? All right, so if we go to the first example here, it says, in general, a point P with coordinates x, y can be mapped to its image point, which we're calling P prime, with coordinates x prime and y prime, using a two-dimensional transformation, which we're calling T. Okay, so notice the notation here. T is the transformation rule. There's different types. In the simple sense, you've got rotations, reflections, translations, dilations, things like that, okay? So T is the transformation. It's mapping point xy, the point with coordinates xy, to a second point P prime with coordinates x prime, y prime. So that's what that notation means. All right, here we have a triangle with vertices A, B, and C. Let's plot those to start. So A is at 0, 2, B, 3, 1, C, 2, negative 3. So plot them, and then we're going to label them A, B, C. Connect them to draw the triangle. All right, now I'm going to find triangle A prime, B prime, C prime using the transformation rule that the point of xy should be mapped to x plus 2y, comma, 3x plus y. So one option, you could do this point by point. All right, so let's say for point A, if I use the rule for T here, the point of 0, 2 is going to become the following. So what this means is to get the x coordinate of your new point, you're going to take the original x, 0, and add it with 2 times your original y. To get the y coordinate, you'll use this rule. So that's 3 times your original x added with 2. We simplify both of those. I'll end up with 4, 2. That would be the point A prime. Okay, now I could repeat that for the other points, right? That would get kind of cumbersome. So I would like to be able to be more efficient with this. And that's where matrices can come into play. So what I'm going to do is I'm going to create a system here. The rule x plus 2y is supposed to give me x prime, right? And 3x plus y is supposed to give me y prime. Notice how I just created a system. I can take that and rewrite it as a matrix equation. So it would have a coefficient matrix, 1, 2, 3, 1, multiplied by a variable matrix, xy, equaling another variable matrix, x prime, y prime. Now the coefficient matrix, that's our transformation rule. That's T. And then the first variable matrix, that's for point P, and the second one is for P prime. Okay? So I could use this to insert any coordinates I want for P to get P prime. All right, so let's do it again for A, using this. So I got T, and now I'm going to make this the specific point of A with coordinates 0, 2. A 2 by 2 times a 2 by 1 is going to create a 2 by 1. So think if I go first row with first column, 1 times 0 is 0, added with 2 times 2, I'll get 4. Second row, first column, 3 times 0 is 0, added with 2, I'll get 2. And that gives me A prime, right? Okay, now you might be thinking like, well, how is that any better than what we did up above in green, right? Well, the benefit is I don't have to do this one point at a time. I can put as many points as I want into the variable matrix. Okay, so I'll leave this T as is, 1, 2, 3, 1. And now I'm going to multiply it by a 2 by 3 since I have 3 points. So the columns are going to represent the coordinates of those 3 points. So I've got 0, 2 for A in the first column, 3, 1 for B in the second, and 2, negative 3 for C in the third. And now when I multiply those together, a 2 by 2 with a 2 by 3, it'll create a 2 by 3. And the columns will represent A prime, B prime, and C prime. So we already know the first column, it should give us 4, 2. Okay, what about for B prime? I'll use first row, second column, 1 times 3 is 3. Added with 2 times 1, that's going to give me a 5. That would be the x coordinate for B prime. If I want the y coordinate, I go second row of T with column B here. 3 times 3 is 9. 1 times 1 is 1. Add them together, you get a 10. Okay, and then repeat the process using the third column C there, and you'll end up with negative 4 and 3 as the coordinates for C prime. Okay, so let's plot those. 4, 2. 5, 10. 4, negative 3. I'm sorry, negative 4, positive 3. Looked at that backwards. Okay, and stressing vocabulary here. So the original triangle, ABC, we'll call that our pre-image before the transformation took place, and then the new triangle is known as the image. Okay, now you see how this could be helpful in a programming sense, like if I'm trying to program a video game, especially nowadays with the graphics as intense as they are, right? I could have a bunch of different vertices to represent, a figure, not just 3, okay? And I could organize those within an array like I have here with the matrices, and then perform these types of calculations to make the transformations happen. Questions on that example? Okay, example 2. So here I've got a fish already created for us. I want to transform the fish in this figure. It's we'll call that figure F, using the rule, the transformation rule, that the original point xy maps to 2x negative y. Okay, and we'll take the same approach that we just did. So I'm going to create a system out of this. I'll say the first equation would be 2x plus 0y would equal x prime. The second equation would have to be 0x minus y would equal y prime, right? This is supposed to represent x prime. This is supposed to represent y prime. Translate that into a matrix equation now. The transformation matrix would be 2, 0 in row 1, 0, negative 1 in row 2, multiplying a 2 by 1 of xy equaling a 2 by 1 of x prime, y prime. And I can make this have as many columns as I need it to, right? Depending on the number of vertices in the figure that I'm trying to transform. Okay, so carry down that 2, 0, 0, negative 1. And then we're going to need several columns for the points of figure F here. Okay, so I'm going to start at the point 1, 2. And I'll go, let's go clockwise from there. So the next I'll put in is 2, 3, 3, 3, 4, 4, 4, 3, 5, 3. Okay, so then it comes in. That's going to be 4.5, 2, 5, 1, and 2, 1. Okay, now we start multiplying those out. So if I go first row with first column, that's going to be a 2 plus a 0 or a 2. Second row, first column, 0 plus negative 2 or negative 2. So I'll have 2, negative 2. Let's plot that. Okay, and then we can continue the calculations. I've done it already for us. So next is going to be 4, negative 3. Okay, then after that, 6, negative 3. 8, negative 4. 8, negative 3. 10, negative 3. 9, negative 2. 10, negative 1. And lastly, 4, negative 1. Okay, so now you just got to figure out how to connect them all appropriately. There's our fish. It's now upside down. Okay, now a little bit of investigation here. It says now approximate the areas of F and F prime by counting squares. Ooh, that sounds fun. All right, so let's look at F first. All right, so in the original figure there, looks like, I start breaking this down, I've got 4 full 1 by 1 squares there, right? So my area's got to include a 4. Let me keep track of this down here. Let's say area of F. We'll have to include a 4. Okay, now I could break these up into some triangles, and think to find the area of a triangle you need to do 1/2 times its base times its height, right? So this triangle right here, both the base and the height are 1, agreed? So it would be 1/2 times 1 times 1, or 1/2. And wouldn't that be the same for this triangle and this triangle, the thin? So altogether, I've got 3 triangles whose areas are both 1/2. So I'll say plus 1/2 times 3. Okay, and then on the back of the fish, let me draw in there, the rectangle that I just created, isn't that another area of 1? 1/2 and 1/2, really? Okay, and then the 2 smaller triangles here, area would be 1/2 times the base, which is also 1/2, times the height, which is 1. So that's going to be 1/4, and I got 2 of those, right? So this is 1/4 times 2. Okay, so let's clean that up. We got 4 plus 3/2 plus 1 plus 1/2. What's that all going to equal? 7. 7 square units. Okay, so now let's kind of repeat the process for F prime here. Let me label that. This is F prime. So we'll start with the full squares first. One, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. Okay, I'm going to create a couple triangles here. So both of those would be 1/2 times, what's their base length? 2 times their height, 1. So that means each of those has an area of 1. So I'm going to add on 1 times, and technically I've got 3 of them, don't I? Because of right there as well. So 1 times 3. Okay, and then the only thing left to find are the 2 triangles at the end here. They're both 1/2 times 1 times 1, or 1/2. I've got 2 of those. So this is going to give me 10 plus 3 plus 1, or 14 square units. Okay, now it says to find the ratio of F prime to F. So I should have in there the ratio of the area F prime to F. It's 2, yeah. Okay, now it says to find the determinant of T. Well, what is T? That was our transformation matrix up here, this guy. All right, so the determinant of T, you can represent it like that, or often you'll see it just written with like absolute value around it, around T. That would be 2 times negative 1 minus 0 times 0, which would be negative 2. What do you notice?
The absolute value of the determinant is the same as the ratio.
Yes. If I take the absolute value of that, I get the same value as the ratio of these two areas. And you think that's a coincidence?
Yes.
It is not. It is not a coincidence. If we go to our next page, we actually have a theorem. Okay, let T be a 2 by 2 matrix that represents a linear transformation mapping R onto R prime. Then the determinant of T has to equal the ratio of the areas R prime and R. So that's what we just saw. Okay, now some added parts to this theorem. If the value of the determinant of T is greater than 0, then the image and the pre-image are going to have the same orientation. That was not what happened in our last example. In our last example, the determinant was negative. It was negative 2, right? So notice it says when the determinant is less than 0, the image and the pre-image have opposite orientations. So if we go back, we can verify that. The first fish was obviously facing up. The other fish, after we found F prime, is facing down. Opposite orientations. Okay? And the final part of that theorem, if the determinant is exactly 0, then R prime, the image points, they lie on a line through the origin. Okay? And we have a homework question. I think it's the last problem of the homework for that specific situation for you to see more of what we mean in that regard. Basically, all of the points for R prime, they're going to form a line when you connect them. And that line would have to go through the origin.